We know that the rate of a reaction depends on the concentration of its reactants and the temperature. Along with the concentration and temperature, a catalyst also has a major effect on the rate of a reaction. A catalyst is defined as a substance that alters the rate of a reaction without itself undergoing any permanent chemical change. A catalyst thus can enhance or retard the rate of a reaction. A catalyst that enhances the rate of a reaction is called a positive catalyst, while a catalyst that retards the rate of a reaction is called a negative catalyst. Let us now discuss the characteristics of positive catalysts and their effect on the rate of a reaction. A positive catalyst increases the rate of a chemical reaction, is not consumed by the reaction, does not change the equilibrium constant for the reaction. That is, it shortens the time required to establish equilibrium, but doesn't affect the final position of the equilibrium. Also, a small quantity of the catalyst can catalyze a large quantity of reactants, since it is not consumed during the reaction and can be used again and again. You will understand this better with an example. The hydrogenation of ethene in the presence of nickel yields ethane. In this reaction, nickel acts as a catalyst. Catalysts increase the rate of reactions by providing a new pathway or mechanism that has a lower activation energy, as shown in the diagram here. A larger proportion of the collisions that occur between the reactants now have enough energy to overcome the activation energy for the reaction. Thus, a large number of collisions become effective. As a result, the rate of the reaction increases. Let us see how nickel acts as a catalyst in this reaction. Molecules of hydrogen first get absorbed on the surface of nickel by partial chemical bonds. The greater the surface area of the catalyst, the greater is the rate of the reaction. As a result, the bond between two hydrogen atoms of a hydrogen molecule gets weakened and breaks to form hydrogen atoms. These hydrogen atoms are attached to the surface of nickel by chemical bonds. In the next step, a highly energetic activated complex is said to be formed when these hydrogen atoms attach to ethene molecules by partial chemical bonds. The highly unstable activated complex further dissociates to form molecules of ethane and the free catalyst. Thus, a catalyst increases the rate of a reaction. Now let us arrive at the modified Arrhenius equation on the basis of the collision theory of chemical reactions. The collision theory was proposed individually by Max Strauss in 1916 and William Lewis in 1918. It explains how chemical reactions occur. According to this theory, chemical reactions occur when the hard, spherical molecules of reactants collide with each other. Also, the reactant particles must collide not only with sufficient energy, but also with the correct orientation. Such collisions are referred to as effective collisions. These collisions lead to the formation of the product. To understand this better, consider the collisions with sufficient energy with different orientations between ethyl bromide and hydroxide ion. The collisions in case of B with proper orientation result in the formation of the product ethyl alcohol. the rate constant for a simple biomolecular reaction, as predicted by the collision theory, is K is equal to ZAB multiplied by e to the power minus EA by RT, where ZAB is the collision frequency of reactants A and B, and e to the power minus EA by RT is the fraction of the molecules with activation energy greater than EA. The Z in this equation can be compared to the factor A in the Arrhenius equation. Since all the collisions do not lead to the formation of products, another factor called steric factor, P, is introduced in the collision theory to account for effective collisions. P refers to the collisions between molecules with the proper orientation. Taking the steric factor into consideration, the Arrhenius equation can be modified to K is equal to P multiplied by ZAB multiplied by e to the power minus EA by RT. Thus, in the collision theory, the activation energy and proper orientation of the molecules together determine the criteria for an effective collision, and, therefore, the rate of a chemical reaction.